It is America's own version of the bullet train, the Acela Express. Its name was created from the words acceleration and excellence, and many believe the Acela, with its state-of-the-art design, power, and speed, could revolutionize the way we travel.
The Acela was the truly first new train developed in America in 30 years. So we're basically breaking ground.
Launched in the winter of 2000 at a cost of $800 million, the Acela rockets between Boston and Washington, D.C. at speeds reaching 150 miles an hour. The Acela takes about 2.5 hours to travel between New York and Washington, and 3 hours and 18 minutes from New York to Boston. The New York-Boston leg is now about 90 minutes faster than earlier trains.
It has power to spare. It's kind of the sports car of the industry right now.
During the Acela's journey north of New York, there are so many twists and turns that if you were to fit them together, they would create 10 full circles. The Acela can take the turns at speeds higher than conventional trains because of its unique tilting cars. As the Acela enters a curve, a computer in the lead car adjusts hydraulic jacks in the train's wheel sets. As a result, the passenger cars will tilt by as much as 4 degrees, depending on the speed of the train and sharpness of the curve.
We have a series of transponders that are embedded in the track structure that actually give location to the train, so the train knows what it's supposed to be doing at various locations.
Without this technology, passengers would have to brace themselves for every turn.
The ideal high-speed rail experience is you're in a railroad car, but you're not subject to an acute sensation of speed. There's no drama associated with it.
The Acela belongs to an elite group known as high-speed trains. It's a term roughly defined as passenger trains that travel above 200 kilometers or 125 miles an hour. And like most high-speed trains, the Acela is electrically powered. The benefit is that electric trains tend to be lighter in total weight than diesel locomotives, more economical to operate, and they're able to achieve faster acceleration and stopping. They acquire power from overhead wires called the catenary. A current collector or pantograph carries electricity to an engine that drives the train's traction motors. But as fast as the Acela is, it cannot travel at 150 miles an hour during its entire run. If it could, the Boston to Washington trip might be closer to 4 or even 3 hours. The principal culprit? It shares its route with other trains.
We have numerous areas where we have constrained operation, New York in particular. Literally 1,000 trains go in and out of there during the day, so anything that's moving a lot faster, a lot slower, tends to be an operational problem.
Thousands of people travel on the Acela trains each day, and the number is growing. A one-way ticket from Boston to Washington is under $200. Riders will find large windows that allow light to flood in, oversized adjustable seats, ample legroom, and work tables with electrical outlets.
Ridership is excellent for us. We anticipate growth over the years, and certainly all the features that we've incorporated in this particular train set will be used in train sets that will follow us.
High-speed trains are among today's fastest land vehicles. And yet it was not so long ago in human history that we could only go as fast as our feet or animals could carry us. The ancient Greeks and later the Romans used what might be called the first railroads. They built stone grooves for wagon wheels. By the late medieval period, German miners were using wooden tracks with rails and special wooden wheels to haul lead and tin from mines.
A wheel, whether it's wood or metal or anything else, traveling in the dirt requires a lot of effort to move.
The idea of building tracks spread to other parts of Europe, and eventually rails and wheels were made of cast iron. Then, in the late 1700s, came the invention that would one day revolutionize rail travel: the steam engine.
By the period of 1805 to 1810, it improved enough that boilers could get smaller, and the idea of self-propelled engines, locomotives, became a conceptual possibility.
In 1829, a self-taught mining engineer named George Stephenson turned a conceptual possibility into a reality by creating what would become the standard for steam locomotives around the world. It was called the rocket. The rocket had a smokestack in the front and a boiler with a firebox in the back. The steam it generated would cause pistons to move back and forth in cylinders, which were connected to crank pins on the driving wheels. The rocket could pull dozens of railroad cars weighing hundreds of tons at the unheard-of speed of 20 to 25 miles an hour.
It was the first reliable, long-distance, all-weather form of mechanical land transportation, and it had a transforming effect on England and the rest of the world.
But the new trains after the rocket were far from being the most reliable form of transportation, or the safest, in Europe or the United States.
By the 1840s, locomotive-pulled trains were routinely traveling at 60 and 70 miles an hour on some railroad lines in the United States. This was in an era of primitive braking, fragile wooden cars, poorly constructed, poorly maintained track.
The consequences of any accident were generally catastrophic.
Bridges would burn down that no one would know, and trains would hurtle off them in the dark. Iron bridges would collapse under the weight of trains. The primitive rail might become detached and spring up to the floor of a car and skewer whatever poor occupant happened to be in the way.
For workers on the trains, even the act of slowing down was dangerous. All braking was done by hand.
And the job of the brakeman was to physically apply the brakes by generally turning a wheel that tightened a chain that pulled brake shoes against the wheels of the cars. Well, clearly you couldn't stop the train quickly in an emergency if that was the case.
Then in 1869, George Westinghouse introduced the automatic brake system. His invention used compressed air to apply pressure to brake valves. In the same year, the United States finished building its first transcontinental railroad on May 10, 1869, and the event ignited a railroad boom. In the short period between 1860 and 1900, the network of tracks in the United States grew from 30,000 miles to 200,000 miles.
The steam railroad, which allowed people for the first time to travel unimaginable distances at remarkably high rates of speed, made it conceptually possible to imagine going thousands of miles, of filling this vast continent.
Railroad technology continued to improve, and by the First World War, all the pieces that make up the modern railroad were in place. Automatic air brakes, steel rails, telegraphic communications, automatic track signals, and the steel passenger car.
By the 1920s, it was commonplace for high-speed deluxe passenger trains in this country to routinely travel 70 and 80 miles an hour over short distances. By the 1930s, some railroads were running trains routinely at speeds of over 100 miles an hour, safely and efficiently.
Steam engines dominated the rails. But in the mid-1930s, a new type of locomotive could be seen streaking across the nation: the diesel-electric engine. While not necessarily much faster than steam engines, diesel electrics were more economical,
Steam locomotives were very labor intensive. It took perhaps 2 or 3 hours of service and maintenance for every operating hour, whereas diesel engines, in many respects, were as reliable and simple as an automobile. You turn the key, you fire them up, and you go.
From the beginning, they became industry favorites and were quickly put to work pulling some of America's most glamorous trains. In spite of this efficiency and flourishing of technology, passenger rail service in the United States began to decline. In 1956, the decline gained momentum after President Dwight D. Eisenhower signed the National System of Interstate and Defense Highways Act. The bill would create a network of superhighways, 40,000 miles long. Railroads were left to fend for themselves. And as more Americans turned to their cars and to air travel, rail companies shifted their focus to the more lucrative end of their business, freight service, leaving passenger service to languish.
And finally, in 1971, the government struck a deal with the freight railroads to assume all responsibility for intercity passenger service. And that was the start of the current system, where you have Amtrak as the single national provider of intercity rail service.
On the day Amtrak started operation, it cut the number of daily passenger trains to fewer than 200, effectively reducing service from 43,000 miles to 16,000. Other industrialized nations struggled with what to do with their passenger rail service. And if it weren't for a strong-willed 70-year-old man in Japan named Shinji Sogo, the world's first bullet train might never have been born. Few trains have captured the imagination of the world like Japan's bullet train. These streamlined and futuristic-looking passenger trains race from one end of Japan to the other at speeds ranging from 130 to 186 miles an hour. They carry more than 130 million passengers each year. Ironically, the country with one of the most advanced train systems in the world today was one of the last industrialized nations to have a railroad. Up until the mid-19th century, no one in Japan had ever seen a train. It was only when America's Commodore Perry returned to Japan in 1854 for a second visit that the Japanese got their first glimpse.
Among the gifts that he brought was a toy train, and the Japanese had never seen anything like it, and they were fascinated by the train.
Japan fully embraced Victorian locomotives and rail technology. From 1864 to 1900, railroads were built throughout Japan and soon linked most major cities. By the early 20th century, the government agency overseeing Japan's railroads was the country's largest employer. In 1909, that agency hired graduate student Shinji Sogo. He started out as a minor office clerk, but he would later be known as the father of the bullet train. Sogo was born in 1884 in a small village 31 years after Commodore Perry first landed in Japan. As a student, he attended some of Japan's best schools.
He was a man of a lot of ideas, ingenious, mischievous. When he got to Tokyo to college, he realized the opportunity ahead of him, and he really applied himself.
After landing the job with the railroads, Sogo climbed up through the ranks. By 1930, he was appointed director of the South Manchuria Railway in China. Japan controlled Manchuria after winning the Russo-Japanese War of 1905. They depended on the railroads there for getting food and raw materials back to Japan. But in 1934, Manchuria's political environment became increasingly unstable, and Sogo resigned. He returned to Japan to work as a civil servant until his retirement in 1948. His story might have ended there if it weren't for a crisis in Japan's railroads at the end of World War II.
The Japanese railroads at the time of the surrender in 1945 were in terrible shape. The country had been at war for almost 12 years. The railroads have been overloaded. They had not been maintained.
Tracks, bridges, and safety equipment had deteriorated, and there were few resources available to repair them. Worse still, there was no highway system to speak of, and Japan relied heavily on trains for transportation. They were dangerously overcrowded. Railroad conditions continued to worsen until 1955, when Shinji Sogo was asked to take over as head of Japan National Railways. The decision surprised the nation. He was 70 years old. But Sogo had a vision for Japan's railroads and was determined to see it through.
His chief idea was to build what was called the Shinkansen, which literally means the new rail line. He felt that there was a need for an efficient, high-speed rail line between the two large cities of Osaka and Tokyo.
The new line would cover a distance of 320 miles and be completely dedicated to passenger service. The cost of Sogo's plan would still be astronomical.
Land in Japan is very, very scarce, very, very expensive. They also had to develop a new technology, build new cars, build an electrical system that would provide the power for this kind of a line. And so he knew that he would have a very difficult time getting an appropriation from the government.
To push the project forward, Sogo did two things. He gave a false, low-cost estimate to win government support. And then he did what most entrepreneurs do, got a loan. Sogo convinced the World Bank that Japan was still a developing nation, and he received $80 million. In the meantime, Sogo's engineers went to work.
What they did is they took proven technology being used in Japan and essentially spruced it up and put a new image on it. The trains are what we call electrical multiple unit trains. They're not that much different than what you'd find in any electrified commuter railway. They put bigger traction motors and better running gear under there for the higher speeds, different gearing.
On most trains, heavy traction motors are found in the lead car. What engineers in Japan did was distribute the traction motors throughout the entire train, cutting down the weight in front. The weight distribution tactic of putting motors in every car also gave the train a high horsepower to weight ratio. This made the Shinkansen very fast. It would remain a key design feature in all Japanese high-speed trains to follow. This and every step of development was methodical and pragmatic.
This was not a research program. This was a viable transportation project that solved a circulation and transportation needs. They built it fast, and they didn't want to take any risk. But they were smart, and they went out and hired a good industrial designer to put a nose on this train, and hence the term bullet train became the legacy of the railway business.
The bullet train was officially launched on October 1964. It was an instant success.
Everybody wanted bullet trains. And that's truly probably the only train that looked like a bullet, but everything that's come after that is still called a bullet train. And they basically pushed their envelope from, let's say, 90 miles an hour to 120. It was very high speed for 1964. It created a fantasy that all these other countries, the United States included, said, we have to do that too.
In 1981, Sogo died of pneumonia at age 97. But before his death, he received Japan's highest civilian award. Since the first Tokyo-Osaka line in 1964, Japan has continually added to its high-speed network and replaced its old trains with new. Today, there are more than 1,000 miles of high-speed lines and 360 bullet trains that serve 350,000 passengers each day.
They're now up over 200 miles an hour in some of the sections. They've gone to more higher horsepower train sets. The newest trains are very space age in that they've been designed for the minimum aerodynamic drag. Some people say that this can't be real, but they're out there and running.
They have carried more than 2.8 billion passengers without a single fatality. There are no grade crossings or extreme curves. Both measures reduce the chance of collision or derailment. Furthermore, unlike America's high-speed Acela, it does not share its tracks with slower freight or passenger trains. There's also an army of several hundred workers inspecting the length of the track each night. Overhead wires are checked and track is replaced. And every 10 days, a train called Dr. Yellow runs diagnostic tests on both rail and wire using electronic monitoring equipment. One of the newest trains in service is the Nozomi Series 700 train. Nozomi's operating speed is about 177 miles per hour, but it's capable of reaching 200. It's aerodynamically designed with a flattened nose that actually prevents the train from lifting up. At 708 tons and made with a lightweight aluminum alloy, the Nozomi is Japan's lightest train yet. But as light and swift as the Nozomi is, there's something faster. It's called the TGV, or Train à Grande Vitesse. It's French for high-speed train, and in any language, it moves. The fastest conventional train in the world today is a TGV, or Train à Grande Vitesse. In 1990, the TGV Atlantique broke all records by reaching 320 miles an hour. The speed of a regularly scheduled TGV is considerably slower, but the train still turns heads when flying through the countryside at a cruising speed of 186 miles an hour. The TGV was introduced in 1981 by the French National Railways, or SNCF. The trains are here today because of steps taken in the 1960s by the agency to head off a crisis in the French railroad industry.
The French railroads were condemned. I mean, if you don't improve yourself at a time where you have a big expansion of road and air travel, you just disappear.
Unlike passenger trains in the United States, French trains were still one of the most popular forms of transportation in France. But ridership on lines between the largest cities was at the saturation point. In addition, train cars were decades old.
So for the SNCF management, it was quite a challenge, not only to manage the day-to-day business, but also to come up with a vision for the future that would be compelling and exciting enough.
Remember, in the 60s, Concorde was being built. There was a great expansion of the highways in France. And you want the railroads not to do anything to react about that? They have to invent something.
One idea was the Aerotrain. It was a jet-powered train that ran on a cushion of air, much like a hovercraft. In experiments, it had reached speeds over 100 miles an hour and had a great deal of support because it was futuristic. But it was the less exotic turbo trains that won out. French engineers were certain they could create a train with even greater speed and performance. And in early 1970, they developed the TGV 001. In 1972, powered by a gas turbine, the TGV 001 set a world record with the incredible speed of 198 miles an hour.
The TGV was an absolute revolution. It was the end result of the ability to master technology to a point that was not conceivable in most minds before.
Engineers had created a train that was light in weight and harnessed it to a powerful engine. To cut down on tonnage, they reduced the number of axles. Most conventional trains have a pair of 2-axle trucks per car. On a TGV, the axles are shared. The ends of 2 cars rest on a common axle truck. Aerodynamics are improved due to the lower weight of the train and smaller gaps between cars. This design is present in all TGVs. But the global oil crisis of 1973 suddenly made turbo TGVs very costly. During the same year, the TGV became electric, and like the bullet train in Japan, the TGV would obtain its power from overhead wires.
In order to exploit the technology possibilities of the TGV concept, there was a need to build new tracks.
The SNCF chose to build a dedicated high-speed route 256 miles long between Paris and France's second-largest city, Lyon. Construction began in 1976. Costs would be kept down because the new line would use existing tracks for the first 18 miles outside of Paris and share the infrastructure of 2 roadways, eliminating the need for extensive excavation. The rest of the route would be a straight shot, crossing vast open stretches of countryside. The first section of high-speed rail between Paris and Lyon opened September 27, 1981, and TGVs painted bright orange were soon running 164 miles an hour along its rails. They won rave reviews.
I think that train had in itself such an emotional content. It has definitely led the way for many other projects, not only in France, but also in Europe.
Today, France has the world's most extensive network of high-speed rail in the world. It's a country about the size of Texas, but has nearly 1,000 miles of high-speed track, and its network is growing.
The success has been astounding. And with the link from Paris to the Channel Tunnel toward England, they now have high-speed rail from coast at the English Channel to coast on the Mediterranean.
TGVs have also proven to be safe. After more than 20 years of operation and over 17 million riders a year, there have been no fatalities. So successful, they've spawned an entire industry in France. From a workshop outside of Paris that provides daily maintenance, to the Alstom factory in the coastal town of La Rochelle that manufactures double-decker TGVs.
You cannot fault the French for not doing a fine job, a quality job in putting out a product that's been basically one of the models of the world. And if you ever want to sell a train system here, you point to France and say, we ought to have that too.
And while today's high-speed trains like the TGV provide the fastest rail service in the world, there are many who believe there's a quicker way for trains to travel. One that doesn't involve steel wheels or rail. On April 14, 1999, an experimental train in Japan called the MLX-01 smashed a world speed record. Traveling at an astonishing 345 miles per hour, no wheels guided its movement, and no engine powered its cars. It moved entirely by magnetic force. The train is known as a maglev. There are no maglevs in commercial service in the world today, but Japan, China, and even companies in Germany and the United States hope to change that. The idea behind maglevs is simple. Put 2 attracting magnets near each other and they clamp together. Try the same thing with two repelling magnets and they push apart. This principle is used to levitate trains and guide trains above a special track. Maglevs run on a special guideway lined with magnets that change polarity from north to south. The maglev is propelled forward as magnets in the guideway attract and repel magnets located on the train.
It's an incredibly quiet ride because you don't really hear them go by. You hear the rush of the wind, but since there's no moving motor, it's all magnetic, all you hear is the aerodynamic noise.
There is no friction, there is no contact, on the infrastructure. So there are a lot of benefits at first, around the concept. The only issue I personally see, with the maglev is it is absolutely not compatible with anything that exists today.
The idea that it is so different has attracted supporters. It may be the first new transportation technology in 100 years.
There were some inventions in this country and ideas that magnetic forces can be used for accelerating and powering the vehicles. But it was really Germany in the 1970s that began to apply that and to build magnetic levitation vehicles.
Today, a German company called Transrapid conducts maglev studies on this 20-mile track in Emsland, West Germany. The levitation magnets on the Transrapid system are located on the train's wraparound arms and on the guideway. These magnets propel the train. They also keep the train suspended with magnets on the side. Together, they keep the train at a uniform distance of 10 millimeters from the guideway. Transrapid engineers have run the train to speeds of up to 271 miles per hour. They claim it could go even faster if it weren't for the short distance of their track. Germany has poured more than $1 billion into the Transrapid program, but the country recently scrapped plans to build a maglev between Berlin and Hamburg. The cost of the planned 185-mile-long guideway was cited as being too high.
If you try and do something exotic that's different, that's not compatible with what you've got to spend humongous amounts of money because you have to build it all. That's one of the issues with maglev. You have to build the entire system out to get where you want to go.
In 2001, Transrapid exported its maglev technology to China. The government plans to build a maglev line that will carry 600 travelers 18 miles from the Shanghai airport to its financial district. The trip is scheduled to take just 7 minutes on trains that will run over 200 miles an hour. Shanghai could see its first commercial maglev up and running by 2003. After nearly 30 years of research, Japan is still working to perfect its maglev. Today's experiments are conducted on this 27-mile track west of Tokyo. The testing that's scheduled there is expected to take several more years. In the U.S., however, a maglev system could be operating much earlier. A company called American Maglev broke ground on a new maglev system that will carry students across campus at Old Dominion University in Norfolk, Virginia. As many as 100 students will board this vehicle. It will travel a distance of about a mile and complete its journey in 2 minutes and 3 seconds. And there could be more maglev projects here in the United States. Cities are vying for development money from the Department of Transportation to develop their own maglev systems.
We were given the authority and some funds to begin choosing places where a maglev demonstration project would actually work. The two sites that have been chosen for further development are Baltimore, Washington, and Pittsburgh.
But critics believe that maglevs offer few advantages over high-speed rail trains.
The main image that maglev has is that it is much higher speed than conventional rail and high-speed rail. That used to be true maybe 30 years ago when railroads were traveling up to 100 miles per hour only. Now, with the advancement of railroads, the difference between the two is really very small.
The future of maglev development remains uncertain, but the quest for better passenger travel continues. And tomorrow's trains might well travel under oceans and link our hemispheres. The 21st century has arrived, and futurists are pondering what form the next generation of high-speed trains will take. In Switzerland, plans are underway to develop what's called the Swiss Metro project. The idea is to propel pressurized levitation vehicles at 250 miles an hour in tube tunnels located deep in the earth. All air in the tunnels is removed to create a partial vacuum. The vehicle will be propelled by a system similar to a maglev. Electromagnets will be used to levitate and guide it. Switching the trains to different tunnels will be achieved by a mechanism similar to the chamber of a gun. The creators of Swiss Metro envision a system of tunnels linking all its major cities and eventually all of Europe. They also believe it could be used to link continents. A preliminary study shows that the Swiss Metro is technically feasible and economically viable, and backers hope to link at least 2 cities by 2010. But those who follow the industry predict that the train of the future will be a little less exotic. Because building a new rail infrastructure is so costly, today's trend is to get high-speed or high-performance trains on non-high-speed rail. France's TGVs are capable of running on both AC and DC power, as well as 3 different electrical systems, so that they can run on other older non-high-speed lines that are electrified. Japan has imported high-speed diesel trains from England to run on its older non-electrified routes. In the United States, efforts are also underway to get faster trains on slower non-electrified rail lines. At the Transportation Technology Center in Pueblo, Colorado, tests were conducted on a turbine electric train designed by the Canadian manufacturer Bombardier. The train is powered by a jet engine turbine and is capable of operating at 150 miles per hour. That performance puts it in the company of many of today's high-speed trains.
The turbine engines that are out there are putting out much more power with much less fuel use and pollution. That has a lot of appeal for urban areas that are looking at these kind of intercity travel.
The states of Florida, California, Michigan, and others are all working to develop their own high-speed lines.
Many states are looking at any variety of options. There are some places that maglev is going to work. There are other places where a electrified system would make more sense. And then there are other places in the country where a non-electric version would probably make more sense.
European companies hope to build trains for this new American market. Bombardier and French company Alstom collaborated on the Acela. And now the manufacturers Talgo in Spain and Siemens, builders of Germany's trains, are competing to build other high-speed trains in this country. Whether the high-speed train of the future is electric or turbine, diesel, or propelled by magnets, it will be designed to wow and woo customers.
In a long-distance train or a high-speed train, it's very different. It should be a richer experience with perhaps more textures or more color. I go after creating an environment that will really inspire you, and you're going to want to tell your friends, you should ride that train.
The French with the TGV have always known the importance of design and have used it to market their trains.
When you board a TGV today, you feel like you're not boarding any train. you're boarding a very, very different type of train. So it's hard to explain, but I think it is in a way at the core also of the success of the product.
Japan is no different. From the first bullet train in 1964 to the Nozomi 700 series, their trains convey speed and efficiency. Alstom's AGV is a new train that hasn't yet hit the market. It was designed not only for high-speed performance, but also to promote an image of speed and comfort.
Railroads have been with us a long time, probably be here a long time to come. Will they look different? Most likely. But the basic need is still there. It's a seat that's environmentally comfortable, heating, cooling, some degree of food service if the trip is long enough. These are basic comforts. The transportation system that meets those needs will be a success.
For the high-speed rail industry in Europe and Japan, it used to be all about improving travel time. Today's speed is no longer the focus. Like the automobile and passenger jet industries, train companies are focusing on fine-tuning their products, making them more cost-efficient and safer. In fact, many believe there is a point when fast is too fast.
It's very exciting to be able to go faster and even faster, but there will be a point where certain speeds are unreasonable because the communities that you're serving are too close for that speed, for the ride to be worth the ride.
There's also a financial consideration. The cost of maintenance on both train and track significantly rises with speed. But as manufacturers and designers work through these problems, the number of high-speed train networks will continue to expand. Europe and Asia show tremendous growth. What will happen in the United States is still up for speculation. We can only assume that, like today's bullet trains, trains of the future in America and the rest of the world will get us to our destinations safely, in comfort, and faster than we ever dreamed possible.
There are always going to be surprises.
You don't have to speak the language to be able to interact with people.
Knowing that can make you look at history in a new and exciting way.